this is in continuation of my previous talk, where we have discussed infinite series of real numbers and its convergence or divergence. The discussion was supported by giving few examples. We will continue the discussion further by giving few more convergence criteria for infinite series of positive real numbers. First, we prove an important theorem on convergence criteria of the series sigma x n 1 to infinity, and then we will drive as a corollary many other results which are helpful in identifying the nature of the series. So, these are now there are some criteria for the divergence. So, this we call it as a divergence criteria. Divergence criteria. If a sequence x, say x n of real numbers has either of the following properties, then x is divergent. What is the first is x has two convergent subsequences, x dash, which is say x n k and x double dash, say x r k, whose limits are not equal. And second one is x is unbounded. Okay. The proof is very simple. If a sequence x n of real number has either of the following property, then x is diverging. So, what is this property? First property says, if the sequence x has two convergent subsequences whose limits are not equal, then the sequence will be considered as a diverging sequence. Or second one is, if x is unbounded, that is the limit of x n will go to either plus infinity or minus infinity, then also sequence is considered to be a diverging sequence. The proof follows immediately from the fact that if suppose x is a convergent sequence, then in case of the convergent sequence, any subsequence of the convergent sequence must be convergent and converge to the same limit, because the limit is unique. So, if x any sequence have a different limit along the different subsequences, different path, then the sequence cannot be a convergent one. So, it has to be divergent. Similarly, every convergent sequence is a bounded sequence. So, if a sequence is unbounded, it cannot be convergent. So, proof first is follows, since all subsequences of a convergent sequence x equal to x n, say all subsequences of convergent sequence must converge to the same limit. This is the criteria for the convergence, is it not? That is what we have proved also. This is proved earlier, proved it. So, if a sequence has a subsequence, if it does not converge, then obviously it will be diverging. So, first criteria, first condition shows that the sequence x n is diverging. divergent. Second follows, since a convergence sequence is bounded, is always bounded sequence. So, if a sequence is unbounded, then it must be it must not be it will not be a convergence sequence. Now, here we are not saying boundedness, because even a diverging sequence may be a bounded sequence. So, we are not saying, what we are saying is a convergence sequence will always be bounded sequence. So, once it is unbounded, definitely that sequence will be a diverging sequence. So, that proof follows you. Okay. So, this criteria I think we have given already examples taken. For example, if we take a sequence x n which is minus 1 to the power n, this is sequence, then this has a two limit 1 and minus 1 when n is even and when is odd. So, it is a diverging sequence. And second, if I take the sequence x n to be, say, like this, 1 half 3 1 by 4 and so on. So, this sequence, when there is odd numbers, it will go to infinity when n is odd, and when n is even, then it will go to 0, because half 1 by 4 1 by 8 6 1 by 8 and so on. So, when n is even, so it has the two limits. Okay. Therefore, it will not be a convergent, okay, diverging sequence. Now, we have, for the monotonic sequences, we have a criteria that every bounded monotone sequence is convergent, and that is called the sequence monotonic convergence. Bounded sequence of monotonic sequence are always convergent, and based on this we have a monotone subsequence theorem. That theorem says that if x n is a real number, then there is a subsequence of x that is monotone. In fact, if a sequence is given, then it is not necessary that sequence be a monotone sequence, but always we can identify at least a subsequence which has a which will be a monotone. So, every sequence of the real number have a monotone subsequence. So, that we know that every sequence of real numbers will have a subsequence, that is monotone, either monotone increasing, monotone decreasing and so on. So, once it is monotone and if it is bounded, then that particular sequence will be monotone sequence will be convergent, but it does not mean that sequence x n will be convergent, because the sequence x n does not have all the subsequences which are monotone. So, you cannot say the sequence itself is a convergent one. Okay. Only one particular subsequence which comes out to be a monotone sequence, and if it is bounded sequence, it will converge, if it is unbounded, it will diverge, like that. So, again the criteria for the monotone will not help you much, unless the sequence is monotone, we are unable to identify whether the sequence is convergent or not. And there is one result which also we have seen, the Bolzano-Weierstrass theorem. This theorem we have shown a bounded sequence of real numbers has a convergent subsequence. So, both these result, that is monotonic subsequence theorem, this is the monotone subsequence theorem, and Bolzano-Weierstrass theorem, though it gives a rough idea about this some of the subsequences, but it does not give the total idea about the entire sequence. So, we are unable to get this whether the sequence is convergent, but the Cauchy has given his idea, which is known as the Cauchy convergence criteria, which without calculating the limit of the sequence, which can tell whether sequence is convergent or not. So, for this we will develop first few results and then go. Let x be a sequence of real number. Real numbers, and let x dash be a subsequence. X dash is a and let x dash is a subsequence be a subsequence of x. Now, if we consider x dash as independent sequence, then basically it is also a sequence. So, again we can identify a subsequence of x dash again. So, we can get let x double dash, but x double dash is itself a sequence. So, we can identify that. So, let x double dash be a subsequence of x dash. Then obviously, the element of x double dash are also element of x. So, obviously, x double dash will also be a subsequence of x. Is it okay? So, this and continue like this till we get this. Okay. Now, we have a very interesting result. The result is theorem. The theorem says let x, which is x n, be a bounded sequence of real number. Sequence of real numbers, bounded sequence of real numbers, and let x and x is a belongs to R, and let x belongs to R have the property that every convergent subsequence every convergent subsequence of x converges to x, and let x belongs to have the property that every convergent subsequence of x converges to x. Then the sequence x, then the sequence capital X converges, which is x n, converges to x. Now, this is the converse part of the previous results. In the previous result, we have shown that if a sequence is convergent, then all of its subsequences will be convergent and converge to the same limit. Now, this shows the converse part. Suppose a sequence is bounded sequence, and if all of its subsequences converges to the same point x, then the sequence must be a convergent one. So, proof is now given that x n is a bounded sequence, given the sequence x n is bounded. So, it means all the terms of the sequence are dominated are less than equal to some number. So, there exists an m greater than 0 such that all the terms of the sequence is less than equal to m for all n. for all n belongs to n, because it is a boundary. Now, we wanted the x n is convergent. So, suppose this sequence x n is not convergent, to x, is not convergent to x, is not convergent and to the x point, convergent and converges to x and not convergent to x. Okay. Then what do we, once the sequence is not convergent, does not converge to x. So, we will apply the criteria which we had discussed for the diverging sequence. Then by the criteria we can say, so there exists an epsilon naught greater than 0 and a subsequence x dash which is x n k of x such that x n k minus x is greater than equal to epsilon naught for all k belongs to a set of natural number n belongs to n. Is it on? So, let it be 1. Now, x dash is a subsequence, an element of x dash is also the element of x, and x is given to be bounded. So, the element of the subsequence is also bounded. So, since the x dash is a subsequence of x which is bounded given, so all the terms of the sequence x n dash is also less than equal to m for all k belongs to n. This criteria will help. Now, this subsequence is a bounded sequence. So, x dash itself is a sequence. Now, this sequence is a bounded sequence. Once it is a bounded sequence, then by Bolzano-Weierstrass theorem, a bounded sequence of real number has a convergent subsequence. Okay. So, by Bolzano-Weierstrass theorem, this convergent subsequence. So, by Bolzano-Weierstrass theorem, we can say that x dash has a convergent subsequence x double dash, say x r k, convergent subsequence x double dash r k. Okay. But this x double dash is also a subset, elements of this are the elements of x, but x double dash is also a subsequence of x, and this sequence has a subsequence which is convergent, is it not? So, this subsequence converges, therefore, what we get? So, by this, so this implies that for a given epsilon naught greater than 0, there exists an integer capital say k depends on epsilon naught such that mod of x r k minus x is less than epsilon naught, is it not? But for all k belongs to capital N, let it be 2. Now, first and 2 are contradictory. This first is x n k minus x k is greater than epsilon for. Now, this n k covers all k, because all k is one of the n k's, because this x r k is a subsequence of x n k. So, these are the points belongs to x dash. So, they are also satisfy the condition 1, but this they are also satisfying 2. So, a contradiction to 1. So, a contradiction to 1 proves that. So, why it is contradiction? Because our assumption is wrong that x n is not convergent. Proves that sequence x n is convergent. X n converges to x. This is what we have. Okay. So, this now let us come to Cauchy convergence criteria. Okay. Criteria. Now, this Cauchy convergence criteria tells this tells about the convergence of a sequence x n of real or complex numbers without computing their limit. Limits, because what happens is, if the sequence x n is given, then one can easily identify by taking the limit. If I consider the limit of the sequence, and if the limit comes out to a finite quantity, limit exists, comes out to a finite quantity, then we say the sequence is convergent. But if the limit goes to infinity or does not exist, means along different subsequence different limits, then we say the sequence diverges. But what the Cauchy convergence criteria says, that you need not to compute the limits of a sequence x n, just simply apply that criteria which is given by Cauchy. One can identify whether the given sequence is a convergent one or diverging one. Okay. So, that is the very advantage of this Cauchy convergence criteria, because the previous criteria which we have seen, whether it is a monotonic convergence theorem or maybe a Bolzano-Weierstrass theorem, all these theorem depends on certain particular cases. Say monotone convergence, unless it is sequence is monotone and bounded, you cannot say it is a convergent sequence. Okay. Bolzano-Weierstrass theorem, a bounded sequence has a convergent subsequence, but does not say about the sequence itself, whether the sequence is convergent or not. So, this Cauchy convergence criteria is very interesting and important, and it directly relates to the convergence part of the sequence. So, we will go in detail next class for this. Okay. Thank you very much.